This video is a continuation of drawing Lewis structures using some simple math operations. So far I've already dealt with drawing these with external halogens by way of the CHT-BPE method, and then drawing some that don't violate the octet by way of a process called ANBBLP. And now we're going to deal with some oxyions that may violate the octet, some of them may not. And I have an acronym for this, but I'll also demonstrate a way to do this without the acronym as well. So the first one I'm going to do here is nitrate. And in order to do this, we're going to use an acronym called CBLOP, C-B-L-O-P. And when we go through this process, the C stands for the number of valence electrons around the central atom, which is going to be 5 for the nitrogen. The B stands for bonds, and that's where we got to take a look at what's going on with the nitrogen in this compound, or in this particular polyatomic ion. So oxygen in this is the more electronegative, so oxygen is a -2, which gives us an oxygen charge of -6. Now if the ion is a net -1, that means the nitrogen is a +5. So nitrogen in this particular polyatomic ion essentially is losing all 5 of its valence electrons. There's no sublevel shielding or anything like that we might see in some of these others that could also be other potential essay questions. So then the next number here is in fact that number that we come up with. So that is a 5 as well. The L stands for lone pairs on the central atom, which we take the first 5 minus the second. We got 5 around the center. 5 of them are going to be in bonds. And then, of course, that's 0, but we would divide that by 2 if we had a number there to give us the lone pairs. Here, there are no lone pairs on that central nitrogen. The next thing stands for the oxygen, and this is the oxygen's electrons plus any additional electrons that we may have. So there are 3 oxygens. Each one has 6 valence electrons, so that is 18, plus 1 additional electron because this is a polyatomic ion with a -1 charge. We get a grand total here of 19. The final part of this calculation is the pairs on the oxygens, which is O, 19, minus B, which is 5, which equals 14, and then we're going to divide that by 2 to get the lone pairs on the oxygens, which happens to be 7. So I now know that I'm going to have 5 bonds, I'm going to have 7 lone pairs on the external oxygens, no lone pairs on the central nitrogen. So I draw my central nitrogen, single bond, the oxygen's on, there's 2 more bonds, it does have delocalized pi bonds, and then the final step, no lone pairs on the nitrogen. On the other hand, we do have 7 lone pairs, so oxygen on the right hand side has 2, 4, 5, 6, 7, 8, same thing over here. The bottom one's going to have 3 lone pairs, so that is our total of 7 lone pairs, and brackets and a -1. Now you can do this one without the CBLOP acronym. It's the way I've taught it for a long time, but since all my other drawings deal with using acronyms to draw them, I'm going to go ahead and show you this one with the acronym with CBLOP, but also without it. We can draw this simply with some of the same math involved. Nitrogen in nitrate is a 5 charge, so that tells me that nitrogen is going to have 5 bonds. Nitrogen only has 5 valence electrons, so I'm going to start bonding on these oxygens, 1 and 1 and 1. Got 2 more here, so that means there's going to be a double bond and a double bond. And then again, we're going to go back and we're going to go ahead and finish out the external oxygens. And I know that drawing's kind of rough because I started there with a dot diagram, but again, it's going to look the same way. We're going to have this central nitrogen, double bond oxygen, double bond to an oxygen, single bond to an oxygen, lone pairs like such. And there's a quick check for this as well. It has to do with looking at this charge that we have outside of the brackets when we're done. That's also how many single bonded oxygen you're going to have, because that single bonded oxygen has that extra electron. Oxygen has 6, but if we take a look, this oxygen has 6 plus 1 here that's part of that bond, so there's an extra oxygen there, so the charge on our polyatomic oxyions is going to actually give us the number of single bonded oxygens as well. So that's a way to do this without the CBLOP acronym. So I'll do another one here using the CBLOP acronym. Again, this is now sulfite. This one will be a little bit different. C is the valence electrons on the central atom, which is 6. B is going to be my bond. So again, now I'm looking at this sulfur. What is sulfur in this? Each oxygen is -2, so that's a -6. It's a -2 overall, so sulfur has to be a +4. Again, why that happens on sulfur, if I just take a look at the dot diagram doesn't fully do this justice, but we're losing these electrons, not these two. We're losing the p sublevel electrons, not the s sublevel electrons, because of sublevel shielding. It's slightly less energy to remove p electrons than it is s electrons, slightly, and you can see that with photoelectron spectroscopy. Anyhow, so that gives us 4 bonds, and now we're ready to do the lone pairs. That's our L of this, and that would be 6 minus 4 is 2, divide by 2, so there's 1 lone pair on the central sulfur. And now we're ready to do the oxygens. There are 3 oxygens times 6 electrons on each. That's 18 plus 2 more electrons because it is a polyatomic ion with a -2 charge. That gives me a total of 20. And then lastly, the P is 20 minus 4 of these that are taken care of by way of the bonds, which is 16 divided by 2, 8 pairs of electrons. So 4 bonds on the central atom, 1 lone pair on the central atom, 8 pairs of electrons on the external oxygens that we have. Central sulfur. And we've got 1 more bond. It is also delocalized pi bond. And we do have a lone pair here on the sulfur in the middle as well. 8 pairs on the oxygens. 1 pair, 2 pairs, 3, 4, 5, 6, 7, and 8, brackets, and formal charge. And again, you see here that sulfur is contributing 4 electrons to this particular polyatomic ion, and also the -2 charge. That again tells us that there will be 2 of these oxygens that will be single bonded only, and that's because they have that extra electron accounted for there by way of the charge. So that's the C-block process for drawing these, and this last one I'll do, I'll go ahead and just run through it without actually using the acronym. The acronym works. As a matter of fact, this one doesn't end up violating the octet, so you can actually draw carbonate also by the ANBBLP method as long as you account for the formal charge. In carbonate, just taking a quick look at it to try to draw it without actually doing the acronym, the carbon is a 4 charge in that. So we've got our carbon, bond to the oxygen, to the oxygen, to the oxygen. There is 1 more because carbon is a 4 charge, and carbon only has 4 electrons, so there are no lone pairs on the central carbon. So we get one of those double bonds, actually not a double bond, a delocalized pi bond that can be any of 3 places because there are 3 major resonance contributors, giving that a bond order of 1.3. Good comparison to talk about the carbon-oxygen bond length maybe in carbon monoxide compared to the carbonate ion. Carbon monoxide is triple bonded. That's going to be shorter and stronger than something with a bond order of 1.3. Bond order of carbon monoxide is 3 because it's triple bonded. Again, here we got a bond order of 1.3 because it's a delocalized pi bond among 3 major resonance contributors. Going back to finish out the oxygens, notice there are 2 single bonded oxygens, each with 3 pairs of electrons, 1 double, brackets, -2 charge, and again the -2 charge gives us an indication that there will be 2 of those single bonded oxygens when we draw that. Again, that's just the drawing. That bond is in fact delocalized. So there's our drawing for the carbonate polyatomic ion.